Hello, and welcome to the presentation of a paper Deep Counter-Strike, Counter-Adversarial Deep Reinforcement Learning for Defense Against Metamorphic Ransomware Swarm Attack. My name is Mohit Sewak. Now let's define our threat scenario better. So there are two types of malware, the first generation and the second generation malware. The first generation malware could be easily identified and caught by using signature matching, and more complex first generation malware could be identified and captured using machine learning techniques. But now with the event of metamorphic malware, these malware are very advanced and these are put into second generation malware. And what they do is they have internal code structures that will allow them to change their structures with every infection. So even if you train some machine learning algorithms, it may so happen that these machine learning algorithms couldn't identify these change structures. And if this type of a malware were to enter any of the system in a network, it will end up infecting the whole network, because even if the signatures are captured for this particular type of malware, or if due to rapid training, some machine learning solutions could also come up which can identify initial malware, it may not be able to identify subsequent malware. So we present a novel system in which we create an AI systems which is based upon adversarial DRL, deep reinforcement learning, which mimics this process of creating variants of malware. And what's so special is that these malware are created almost similarly as it would be created by a developer by using obfuscations at the individual opcode level. Now, this is important because the file functionality is preserved only at this level and or any of the high levels, not anything below that. Whereas most of the existing systems try to do it at a binary level, which may actually not preserve the file functionality and hence cannot create a malware. And this is also the first applications of advanced reinforcement learning algorithms like the proximal policy optimization in the field of cybersecurity. And we do this to create these simulations and these structures such that we can create something called a counter-adversarial deep reinforcement learning systems, which will learn how to normalize these malware, thereby creating a defense for them.
Now let's understand why this idea is completely revolutionary to create obfuscations for malware to generate second generation malware. So obfuscations are different types of techniques to change the code or the code structure of a particular program, something like a junk code insertion or moving a routine submitted from one place to another in the code or changing the registers of the mechanism. Now, obfuscations could effectively be done at two levels. One is at the programming code level, and the second is at the machinery code, the assembly code level. Anything beyond that doesn't preserve the functionality of a particular file, and the file couldn't actually be assembled back to something that could be executed on that file system. And hence it is very important that we do obfuscations or any sort of a malware generation at this particular stage, otherwise that malware would not have the functionality preserved, and maybe it will not even have the maliciousness or the main type of things that it is doing available. But at this stage, if you want to play, then you have to play at the level of the instruction set, which is large. And if you're talking about sequence of those instruction sets, which actually creates a particular file, then you're talking about a very exponentially high number of action probabilities in those sequences. And that is why it is so tough to create. But if you do not create it at that level, chances are that what you've created is not a malware and just a random noise. In fact, some of the prior art that we cover actually uses random noise to generate those things, and there is no guarantee that this will execute in any system, and that is why it is important.
Now, what are the different novel applications that this combination of AR layer and CADR systems could be used for? So we have two types of advanced attacks. So one type of advanced attack is that by the metamorphic malware or the second generation malware or a ransomware type malware. And then there is another type of advanced attack, which although is used by commodity malware or also called the first generation malware, but these are used in swarms such that they can penetrate any system and create an initial access through which those second generation or advanced malware could be penetrated to that system. But assume that if you can combine both of these scenarios, whereas that we can create a swarm of malware, and the swarm is not of a commodity malware, which is easy to create and develop, but the swarm is of the advanced metamorphic malware or ransomware. So this is one scenario where the system could be used. The second scenario where these systems or the data or the simulations from the system could be used is to train defenses against similar types of attack or other types of voluminous or a type of advanced attacks. And the third system is to create niche type of defenses, which we talk about in this particular paper, which is to create normalizations instead of retraining a malware classifier with the samples are from this system. And we discussed earlier why it is a better idea to do this way.
The type of solution that we present to generate such a sort of ransomware comes broadly under the category of adversarial deep reinforcement learning. So let's understand some of the related work in the area of adversarial attacks and defenses. So adversarial attacks is not a new thing, but it became really popular with the advent of generative adversarial networks, which were the types of networks used in CNNs for different types of fake image generation. Now, this type of networks use something called gradient-based attacks, and gradient-based attacks are mostly white box attacks, which means both the generator and the discriminator has a complete knowledge of each other, such that they can compute the gradients of their embeddings, and using those gradients, they can influence the detection in the wrong direction. Now, most of the deep learning based classifiers are not very robust to these type of attacks, and that is why not many security systems use these without testing their robustness. Then there is second type of adversarial attacks, which is called as score-based attacks. Score-based attacks are mostly black box attacks, which means you do not know the internal working of the classifier, but you may have some provision to understand whether it's a binary classification or a continuous classification, and what is the probability that has been detected for that particular classification. Now, it is not very easy to fool such sort of a system if it is not just like trivial random noise augmentation. But even these systems could be fooled with the advent of reinforcement learning. So a reinforcement learning agent learns how do you fool this system using just the scores in a very black box manner. And there has been some recent advance to it. But most of these reinforcement learning systems work at a very shallow state and action scenarios, because these require a lot of computational power and data. And also the reinforcement learning algorithms itself become very complex if you try to increase the state size or the action size. That is why most of these models, the reinforcement learning ones, are currently being used to test the robustness of a particular systems against evasion by a particular malware, and they couldn't be used to generate malware.
Now, reinforcement learning systems require an environment which mimics a Markov decision process so that this could be trained and then these are deployed into real life scenarios. For the training of this particular system, both for CADR and ADR, we have like similar type of environments, just the positioning of the components are different and the flow is slightly different. So this particular diagram shows the architecture of an ADRL training environment in which we have number one, which is a repository of existing commodity malware, something like an initial access brokers for ransomware, something like a quadbot or similar bumblebee sort of systems. And then we have also the repository of ransomware if we want to actually create a swarm of ransomware themselves that has higher chances of penetration. Then number two component is a challenger system pipeline, which mimics some of the advanced systems that could be deployed for detection of malware into any of the systems. We'll talk more about it in the later slides. Then we have number three, which is a reward function computer. So this is important for to give rewards to a particular agent such that they can learn an effective policy. So these rewards are computed on the basis of how effectively they are learning to create metamorphic variants of a particular malware. Then number fourth is the state generator and transformer. So this would actually change the obfuscation structure or the opcode structure before they actually do a classification of the change structure from the pipeline. Then we have number five as the environment and state resetter. So every time a new malware is started with, it will get into a series of episodes that will make the agent learn how to obfuscate them. So that series of episodes starts with this particular component. Then we have number six as the action receiver. So this particular part, a component receives the action from an agent, and as per that action, it will transform the internal state of the malware. And then number seven is the state reward transmitter. So whatever is the reward that is coming out from the agent's action, this particular component will give it to the agent such that the agent could learn a policy. So this is a design for training the challenger system, and this challenger system is the zoom up version of the component 2 that we showed earlier. So these experiments were done on a very popular data set, and this being a popular data set, multiple baseline and benchmarks exist on this. So we took the best of the baselines available on this data set, and we trained multiple types of classifiers from it, ranging from simple ML classifiers to deep learning classifiers, sequential deep learning, and then recurrent deep learning classifiers. And then we also identify them not only just for the performance on a particular this data set, but also on their adversarial robustness, because in many of these conditions, when we're talking about advanced AI systems and deep learning systems, in security, we also take care of the robustness of these parameters. And based upon these, the best performing pipeline is chosen. Now, in an earlier slide, we showed the architecture of the training environment, and we referred to the agent which will be training against it. So this is the detailed flow of how the training agent learns against this particular environment. So we have a repository of pre-instantiated agents, which could be randomly instantiated or instantiated based upon a particular algorithm. And these would interact with the components 5, 6, 7 of the environment as we covered earlier. So the agent would try to change the opcode structure of a particular malware, and then if it gets modified to an extent such that none of the challenger systems are able to identify that as a malware, that is what we consider as a successful conversion to metamorphic malware. And in that case, that particular sample, along with its identity of the original malware, is stored in the metamorphic malware sample store. And if an agent is able to successfully converge into successful metamorphic variant for multiple files consecutively, then that agent is called a successful agent, and then that agent itself is or its policy per se is stored in a successful agent configuration or the policy store.
We have got very exciting results from the experiment. So we trained several agents, and we trained them over different types of malwares and ransomware. And we found out that on an average across all those malwares, the mean probability of non-detectability has been increased to 0.45, which means when we create a new malware from the existing ones, the probability that it was malware now reduced to this 0.45, and more than one third of the total malware and ransomwares completely evaded the detection, and there were fruitful variants of it which could be used to perpetuate attacks. Also, we saw that this is not a trivial trick that the system or the agent is learning, but we also saw the similarity of it very similar to the actual variant, and this differs from variant to variant, which means that it is learning to create obfuscations and not just a trivial trick.
Similarly, we also find very good results for the CADRL agents, and the CADRL agents was able to raise the detection part of the metamorphic variance by more than zero point 0.6 probability. But one thing that should be noted is because of the complexity of the CADRL task as compared to the ADRL, there it requires a lot of training to actually get to this particular stage, and from there onwards it can still improve more, but then the improvement is highly asymptotic, which means that now you require a lot many samples even just to create a difference of zero point 0.1 in this particular detection of probability. In conclusion, we designed and developed a novel AI-based system that uses specialized adversarial deep reinforcement learning to obfuscate malware at the opcode level and create multiple metamorphic instances of any malware. The system could obfuscate a malware at an opcode level to evade even the best deep learning based detection systems, and also while preserving their file functionalities. The insights from the experiments on the system prove that with minimal effort, that is, with just by inserting some junk codes to the file, new obfuscations with very high metamorphic probability could be generated by the ARDRL system. These obfuscations could evade even some of the best intelligent systems and malware defense systems, even the ones that are very robust against adversarial DL-based attacks. But to achieve this, we had to use very sophisticated reinforcement learning algorithms like the PPO because of the inherent complexity of the task of the MDP that was created with it. And next, towards our end goal of actually trying to create a defense systems against such AI-generated malware, we trained a counter-adversarial deep reinforcement learning agent-based systems. The CADL system learned how to solve the problem of normalizing the metamorphic malware at the assembly code level, and by doing so, the serial system was able to normalize metamorphic malware to the base variant, which existing detection systems can detect, and thereby creating a very potent defense systems against these type of malware. With this, I would like to say thank you to all, and can take any questions if there are any.